What if everything we thought we knew about the universe was just the tip of the iceberg? Picture this. Out there, beyond the farthest stars and galaxies we can see, lies a boundary so mysterious, so baffling, that even the brightest minds in science are left scratching their heads. We call it the edge of the universe, but what does that even mean? Is there truly an end, or does it stretch into infinity? And what secrets does it hold that could rewrite everything we thought we understood about existence? In this video, we're diving into 25 mind-bending mysteries about the edge of the universe, each one more fascinating than the last, from the limits of what we can observe to the strange forces shaping its expansion. These mysteries don't just challenge our knowledge, they force us to rethink the very nature of reality itself. So, are you ready to explore the unknown? Stick around, because by the end of this video, you'll see the cosmos in a whole new light. Let's begin. Now turning to the first mystery, let's explore the observable universe and its limits. The observable universe is the portion of the cosmos we can see from Earth, but it's not the entire universe. Why is that? It all comes down to light and time. Light travels at a finite speed, and the universe has a finite age around 13.8 billion years. This means light from objects farther than that distance hasn't had enough time to reach us yet. Think of it like standing in a vast field at night with a flashlight. You can only see as far as the light reaches, and beyond that, everything remains hidden. This boundary is known as the cosmic horizon, and it's a fascinating reminder of how much of the universe remains unseen. The implications are profound. If we can't observe beyond this limit, we might never know what lies beyond. This cosmic curtain raises questions about the true size and structure of the universe. Could it be infinite, or is there something more waiting just out of reach? As we ponder this mystery, it's clear that the observable universe is just the beginning of a much larger cosmic story. Now stepping into the second mystery, let's uncover the secrets of the cosmic microwave background radiation. Often referred to as the afterglow of the Big Bang, this faint radiation fills the entire universe and serves as a snapshot of its earliest moments. Picture it as the residual heat left over from the explosive birth of the cosmos, now cooled down to just a few degrees above absolute zero after traveling for over 13 billion years. Discovered accidentally in 1965, this radiation has become one of the most crucial pieces of evidence supporting the Big Bang theory. It's like finding an ancient photograph that captures the universe when it was just a baby, mere hundreds of thousands of years old. But what makes it even more fascinating is that it also marks the edge of the observable universe. Beyond this point lies the cosmic dark ages, a time before stars and galaxies formed, shrouded in mystery. The cosmic microwave background radiation not only tells us about the universe's infancy, but also hints at its vast, unseen boundaries. As we study this faint echo from the past, we're reminded of how far our understanding has come and how much more there is to discover about the cosmos. Shifting our gaze to the next enigma, let's explore the ever-expanding nature of the universe. Imagine the cosmos as a balloon being inflated, with galaxies moving farther apart as space itself stretches. This expansion was first discovered in the 1920s when astronomers observed that distant galaxies were receding from us, their light shifting toward the red end of the spectrum. But the real twist came in the late 1990s when scientists found that this expansion isn't just happening, it's accelerating. Enter dark energy, a mysterious force that makes up about 68% of the universe's energy content. Unlike gravity, which pulls things together, dark energy seems to push space apart, driving the universe to expand faster and faster. This raises profound questions about the universe's edge. If the expansion continues indefinitely, will the universe stretch endlessly, becoming colder and more diluted over trillions of years? Or could there be something beyond the observable universe, perhaps regions we'll never be able to see or reach? The expansion challenges our understanding of boundaries, suggesting that the universe might not have a clear edge but instead extends into infinity. As we grapple with these ideas, we're reminded that the cosmos is not only vast but also ever-changing, with dark energy acting as the unseen hand shaping its destiny. Now venturing into the realm of the multiverse, we encounter a concept that stretches the boundaries of our imagination. The multiverse theory suggests that our universe might not be the only one in existence. Instead, it could be just one of countless universes, each with its own unique set of physical laws and constants. This idea challenges our understanding of the universe's edge, as it implies that what we perceive as the boundary of our cosmos might merely be a doorway to an even larger reality. One type of multiverse theory is the bubble universe model. Imagine a cosmic foam where each bubble represents a separate universe, all existing simultaneously but independently. These bubbles could be expanding or contracting, creating an infinite tapestry of universes, each with its own story. Another fascinating idea is the parallel universe concept, which suggests that every possible outcome of a quantum event spawns a new universe. In this scenario, every decision you've ever made might have led to a different universe where the opposite choice was taken. Then there's the brain multiverse, inspired by string theory. This theory proposes that our universe is a three-dimensional brain, floating in a higher dimensional space alongside other brains that could be other universes. Collisions or interactions between these brains might explain cosmic events like the Big Bang itself. What ties all these theories together is the idea that the edge of our universe might not be the end, but rather the beginning of something far greater. If the multiverse exists, then the boundaries we observe are just the limits of our perception, not the limits of reality itself. This opens up mind-bending questions. Are there other versions of us out there? Could universes collide or interact? And if so, what lies beyond the edge? As we ponder these possibilities, we're reminded that the cosmos is not only vast but also layered with mysteries that push the limits of our understanding. The multiverse theory invites us to rethink what we know about existence and the very fabric of reality. Now shifting our focus to the origins of everything, we arrive at one of the most profound questions in cosmology, the starting point of the Big Bang. This moment, often referred to as the birth of our universe, is where all of space, time, and matter emerged from an infinitely dense and hot singularity. But here's the mystery: what existed before this event? The concept of before becomes almost meaningless because time itself began with the Big Bang. Trying to imagine what lies beyond this starting point is like trying to picture what's north of the North Pole. It's a question that defies our everyday understanding. The Big Bang doesn't just challenge our sense of time, it also forces us to rethink the very nature of the universe's edge. If the universe began as a singularity, then its edge isn't a physical boundary but rather a limit of our observable reality. Some theories suggest that the universe might be finite but unbounded, like the surface of a balloon. As you travel in one direction, you might eventually loop back to where you started without ever encountering an edge. Another intriguing idea is that the Big Bang wasn't a unique event. Instead, it could be part of an endless cycle of universes expanding and collapsing, a concept known as the Big Bounce. In this scenario, our universe might have emerged from the collapse of a previous one, and its edge could simply be the transition point between these cosmic cycles. These theories remind us that the Big Bang isn't just a historical event. It's a gateway to deeper mysteries about the structure and limits of the cosmos. As we explore these ideas, we're left with more questions than answers. Could there have been a pre-Big Bang reality? Is our universe just one chapter in an eternal cosmic story? And if so, what lies beyond the edge of this chapter? The Big Bang's starting point isn't just a scientific puzzle. It's a philosophical one that invites us to contemplate the very nature of existence. And as we ponder these questions, we're reminded that the universe's edge isn't just a boundary, it's a frontier of endless possibilities. Now turning to the shape of the universe, we find ourselves faced with a question that is as fascinating as it is mind-bending. Scientists have theorized that the universe could take on one of three primary shapes: flat, spherical, or hyperbolic. Each of these shapes carries profound implications for how we understand the cosmos and its edges. Let's start with the flat universe. Imagine a vast, infinite sheet of paper stretching endlessly in all directions. In this model, the universe has no curvature and parallel lines would never meet. A flat universe suggests that space is infinite, meaning there's no true edge to speak of, just an endless expanse of galaxies, stars, and cosmic wonders. Next, consider the spherical universe. Picture the surface of a globe, where every point is connected in a finite but unbounded space. In this scenario, the universe would have a definite size but no physical edge. If you were to travel in a straight line, you'd eventually loop back to your starting point, much like circumnavigating the Earth. This shape would mean the universe is finite, yet there's no boundary to cross. Finally, there's the hyperbolic universe. This shape is harder to visualize, but imagine a saddle or a potato chip that curves away from itself at every point. In this model, parallel lines would diverge over time, and the universe would expand in a way that creates infinite space. Like the flat universe, a hyperbolic one suggests no true edge, but with a twist. Space itself would stretch and curve in ways that defy our everyday intuition. The shape of the universe isn't just an abstract concept, it holds the key to understanding whether the cosmos is finite or infinite, and whether it has edges or not. Observations of the cosmic microwave background radiation, the afterglow of the Big Bang, suggest that the universe is most likely flat. However, this remains an open question, and scientists continue to explore the evidence with cutting-edge tools like the James Webb Space Telescope. As we ponder these possibilities, we're reminded that the universe's shape is more than a geometric curiosity. It's a window into the very fabric of reality. Whether flat, spherical, or hyperbolic, the shape of the universe challenges us to rethink what we know about space, time, and the boundaries of existence. Stepping into the next cosmic puzzle, we encounter the horizon problem, a mystery that challenges our understanding of how distant parts of the universe came to be so strikingly similar. If we look at regions of space that are billions of light years apart, they share the same temperature and physical properties. But here's the catch: these regions are so far apart that, according to the speed of light, they could never have been in contact with each other. So how did they end up looking so alike? This is where inflation theory steps in. Proposed in the early 1980s, inflation suggests that in the tiniest fraction of a second after the Big Bang, the universe underwent an incredibly rapid expansion. Picture blowing up a balloon to many times its original size in an instant. This explosive growth would have smoothed out the universe, making distant regions appear uniform, even though they were never directly connected. Before inflation, the universe would have been small enough for all regions to be in contact, allowing them to reach a shared temperature. Then, as inflation kicked in, these regions were pushed apart faster than the speed of light, creating the vast distances we see today while preserving their uniformity. Inflation theory not only provides a compelling solution to the horizon problem, but also helps explain other cosmic puzzles, such as the universe's overall flatness and the distribution of galaxies. While it's still a theoretical framework, evidence from observations like the cosmic microwave background radiation supports the idea that inflation could have played a key role in shaping the early universe. As we unravel this mystery, we're reminded of just how interconnected and finely tuned the cosmos appears to be. The horizon problem highlights the delicate balance of forces that shaped our universe, and inflation theory offers a glimpse into the dramatic events that set the stage for everything we see today. With each discovery, we move closer to understanding the true nature of the universe's origins and its edges. Delving deeper into the cosmic enigma, we now turn our attention to dark matter, an invisible force that plays a critical role in shaping the universe's structure and potentially its very edges. Unlike ordinary matter that we can see and interact with, dark matter doesn't emit, absorb, or reflect light, making it invisible to our telescopes, yet its influence is undeniable. Through careful observation, scientists have noticed that galaxies rotate faster than they should based on the visible matter they contain. This discrepancy suggests the presence of an unseen mass, dark matter, providing the gravitational glue that holds galaxies together. Without it, stars on the outer edges of galaxies would simply fly off into space, but dark matter's reach extends far beyond individual galaxies. On a larger scale, it forms a vast web-like structure known as the cosmic web. This network of dark matter acts as a scaffold, guiding the distribution of galaxies and galaxy clusters across the universe. In fact, without dark matter, the universe as we know it would look entirely different. So, what does this mean for the edge of the universe? Dark matter's gravitational influence could shape the boundaries of the cosmos, determining how and where matter accumulates. Some theories suggest that dark matter might even define the outermost limits of the universe, though this remains an open question. Despite its pivotal role, dark matter remains one of the greatest unsolved mysteries in modern science. Researchers are using advanced technologies like particle detectors and space telescopes to uncover its true nature. Whether it's made of undiscovered particles or something entirely unexpected, solving the dark matter puzzle could revolutionize our understanding of the universe's structure and its boundaries. As we explore this invisible force, we're reminded of how much of the cosmos remains hidden from our view. Dark matter not only shapes the universe's edges, but also challenges us to rethink what we know about the fabric of reality itself. And with every discovery, we edge closer to unraveling one of the most profound mysteries of all. Turning our gaze to another cosmic puzzle, let's explore the force that's silently stretching the fabric of the universe, dark energy. While dark matter holds galaxies together, dark energy is doing something entirely different. It's driving the universe to expand at an ever-increasing rate, a discovery that has fundamentally reshaped our understanding of the cosmos. First observed in the late 1990s, dark energy was detected by studying distant supernovae. Scientists expected the universe's expansion to be slowing down due to gravity, but instead they found it was speeding up. This unexpected acceleration pointed to the existence of a mysterious force counteracting gravity, dark energy. So, what is dark energy? The truth is, we don't fully know. It's often described as a property of space itself, a kind of energy inherent to the vacuum of the universe. One leading theory suggests it's linked to what's called the cosmological constant, a concept introduced by Albert Einstein. Think of it as a kind of background energy that's always present, pushing space apart. But the implications of dark energy are staggering. If the universe continues to expand at this accelerated rate, it could lead to a scenario known as the Big Freeze. In this distant future, galaxies would drift so far apart that the universe would become cold, dark, and empty. It's a chilling thought, but one that underscores the profound influence of dark energy on the cosmos. And what does this mean for the edge of the universe? If dark energy keeps stretching space indefinitely, the universe might not have a traditional edge at all. Instead, it could just keep expanding, creating a boundary that's forever out of reach. This raises questions about the ultimate fate of the cosmos and whether there's any limit to how far it can grow. Despite its elusive nature, dark energy is a key piece of the cosmic puzzle. It's thought to make up about 68% of the universe's total energy, dwarfing the contributions of dark matter and ordinary matter combined. Yet, its true nature remains one of the biggest mysteries in modern physics. As we continue to study this enigmatic force, we're reminded of how much of the universe lies beyond our current understanding. Dark energy not only shapes the universe's expansion, but also challenges us to rethink the very nature of space, time, and existence. With every observation and experiment, we inch closer to unlocking the secrets of this invisible driver of cosmic destiny. Shifting our focus to the ultimate fate of the cosmos, we encounter one of the most profound questions in cosmology: how will the universe end? Theories about the universe's demise not only captivate our imagination, but also offer insights into the nature of the universe's edge. Let's explore three leading scenarios: the Big Freeze, the Big Crunch, and the Big Rip. First, the Big Freeze, also known as the heat death, paints a picture of a universe that continues to expand indefinitely. As dark energy drives galaxies farther apart, stars will exhaust their fuel, and black holes will evaporate over unimaginable timescales. Eventually, the universe would become a vast, cold void, devoid of light and heat. In this scenario, the concept of an edge becomes elusive as space itself stretches infinitely, leaving no boundary to define. Next, there's the Big Crunch, a dramatic contrast to the Big Freeze. Here, the universe's expansion slows, stops, and eventually reverses, collapsing back into a single point. This would mirror the Big Bang in reverse, with galaxies and matter drawn together into an unimaginably dense state. If this were to happen, the universe's edge would cease to exist as everything converges into a singularity. Finally, the Big Rip presents a particularly violent end. In this scenario, dark energy's influence grows so strong that it tears apart not just galaxies, but stars, planets, and even atoms themselves. The universe would be shredded into its most fundamental components, with space itself ripped apart. This would leave no edge or boundary, only a fragmented void. Each of these theories offers a unique perspective on the universe's edge. In the Big Freeze, the edge becomes unreachable as space stretches endlessly. In the Big Crunch, the edge collapses inward, disappearing into a singularity. And in the Big Rip, the edge disintegrates entirely, leaving no coherent structure. These scenarios remind us that the universe's edge is not a fixed concept, but one deeply tied to its ultimate fate. Whether it's an infinite expansion, a fiery collapse, or a cosmic unraveling, the end of the universe challenges us to think beyond the limits of our current understanding. As we ponder these possibilities, we're left with a sense of awe and curiosity about the mysteries that lie at the very edge of existence. Now turning to a mind-bending idea that could reshape everything we think we know about the universe, let's dive into the holographic principle. This theory suggests that our entire universe might be a hologram, a projection of information encoded on a two-dimensional surface. Imagine for a moment that the vastness of space, with its billions of galaxies and stars, is not what it seems. Instead, it's like a cosmic movie screen where all the richness of the three-dimensional universe is just a trick of the light, a shadow of something far simpler. At its core, the holographic principle stems from the study of black holes, where scientists discovered that all the information about what falls into a black hole can be stored on its surface. This led to the radical idea that the universe itself might operate in a similar way, with all the information about the cosmos encoded on its outermost boundary. If this is true, then the edge of the universe isn't just a physical limit, it's a kind of cosmic hard drive, storing everything that happens within it. This idea challenges our traditional understanding of the universe's edge. Instead of thinking of it as a place where space and time simply end, the holographic principle suggests it's a dynamic, information-rich surface that contains the entire universe within it. It's as if the universe is a giant puzzle, and its edge holds all the pieces needed to assemble the bigger picture. But how does this affect our perception of reality? If the universe is a hologram, then what we see and experience in three dimensions might be just a projection of deeper, hidden laws. It's a bit like watching a movie. The images on the screen look real, but they're actually created by light passing through a two-dimensional film. In the same way, the holographic principle proposes that the universe's complexity is an illusion, a higher dimensional trick played on our senses. This theory not only shakes up our understanding of the universe's edge, but also forces us to rethink the very nature of reality itself. It suggests that the boundaries we perceive between here and there, now and then, us and the cosmos might not be as solid as they seem. Instead, they could be part of a grander, more interconnected framework, where the edge of the universe is not a limit but a gateway to understanding the deeper truths of existence. As we explore this idea, we're reminded once again that the mysteries of the universe are far stranger and more profound than we can imagine. The holographic principle invites us to look beyond the surface, to question what we think we know, and to embrace the possibility that reality is far more intricate and far more extraordinary than it appears. Now shifting our focus to another fascinating puzzle, let's explore the information paradox. This mystery is deeply tied to black holes and challenges our understanding of how information behaves in the universe. At its heart, the paradox raises a critical question. When something falls into a black hole, what happens to all the information it carries? According to the laws of physics, information cannot be destroyed. Yet, black holes seem to defy this rule, swallowing everything that crosses their event horizon, including the information about what fell in. The problem arises when we consider what happens to a black hole over time. Through a process known as Hawking radiation, black holes slowly evaporate, releasing energy back into the universe. But here's the catch: this radiation appears to be random, carrying no trace of the information that was once inside the black hole. This creates a paradox. If the information is truly lost, it would violate the fundamental principles of quantum mechanics, which state that information must always be preserved. Scientists have proposed various solutions to this paradox, each with profound implications for our understanding of the universe's boundaries. One idea is that the information isn't truly lost but somehow encoded in the Hawking radiation itself, in a way we don't yet fully understand. Another possibility is that the information is stored on the black hole's event horizon, much like how the holographic principle suggests that information about the universe is stored on its edge. The information paradox doesn't just challenge our understanding of black holes, it forces us to rethink the nature of reality itself. It suggests that the boundaries of space and time where black holes exist might operate under rules we're only beginning to uncover. If information can escape a black hole, even in an altered form, it could mean that the universe's boundaries are far more complex and interconnected than we've ever imagined. This mystery also ties into the broader question of how the universe stores and processes information. If black holes can somehow retain or transmit information despite their seemingly destructive nature, it might hint at a deeper, hidden structure to reality, one that could redefine our understanding of the cosmos from its very edges to its core. As we delve deeper into this paradox, we're reminded that the universe is full of questions that push the boundaries of our knowledge. The information paradox not only challenges what we think we know about black holes, but also invites us to consider the possibility that the universe's edges hold secrets far beyond our current comprehension. Now turning our gaze to another profound cosmic mystery, let's consider the Fermi paradox. Named after physicist Enrico Fermi, this paradox highlights a striking contradiction. If the universe is so vast and filled with countless stars and planets, why have we not yet detected any signs of alien civilizations? This question becomes even more intriguing when we think about the universe's edge and what it might mean for life beyond Earth. The universe is estimated to contain hundreds of billions of galaxies, each with hundreds of billions of stars. With such staggering numbers, the probability of other planets hosting intelligent life seems almost certain. Yet, despite decades of searching, from radio telescopes to space probes, we've found no definitive evidence of extraterrestrial civilizations. This absence of contact is what makes the Fermi paradox so perplexing. One possible explanation is that intelligent life is incredibly rare. Even if conditions for life exist, the leap to advanced civilizations capable of communication or space travel might be extraordinarily unlikely. Another theory suggests that advanced civilizations may self-destruct before they can make contact with others, perhaps through environmental collapse, war, or technological disasters. This idea ties into the concept of the Great Filter, a hypothetical barrier that prevents life from progressing to interstellar communication. On the other hand, some scientists propose that alien civilizations might exist but are simply too far away or too different for us to detect. The vast distances of the cosmos could make communication nearly impossible, especially if life exists near the edge of the observable universe, where the expansion of space might stretch signals beyond recognition. The Fermi paradox also invites us to reconsider our place in the universe. Are we alone, or is the universe teeming with life we've yet to discover? This mystery challenges us to think about the nature of life, the limits of communication, and the possibility that the universe's edges might hold secrets we're not yet equipped to uncover. As we ponder this paradox, we're reminded that the universe's vastness is both a source of wonder and a challenge to our understanding. The Fermi paradox not only questions the existence of other civilizations, but also invites us to explore the boundaries of our own knowledge and imagination. Now shifting our focus to another captivating cosmic enigma, let's explore the Great Attractor. This mysterious region of space exerts a powerful gravitational pull, drawing galaxies, including our own Milky Way, toward it at astonishing speeds. Located near the edge of the observable universe, the Great Attractor raises questions about what lies beyond our cosmic horizon and what forces shape the large-scale structure of the universe. The Great Attractor is situated approximately 250 million light-years away, in the direction of the Centaurus and Norma constellations. Despite its immense influence, it remains largely hidden from our view, obscured by the dense band of stars and dust in our galaxy known as the Zone of Avoidance. This obscurity has made studying the Great Attractor a significant challenge for astronomers, but recent advancements in technology are beginning to shed light on its secrets. What makes the Great Attractor so intriguing is its gravitational domination over an enormous region of space. It's not just a single object, but a massive concentration of matter, potentially a supercluster of galaxies that bends the paths of surrounding galaxies toward it. This phenomenon forces us to reconsider our understanding of gravity and the distribution of matter in the universe. One theory suggests that the Great Attractor might be part of an even larger structure, such as the Laniakea supercluster, which encompasses our Milky Way and thousands of other galaxies. If so, it could be just one node in a vast cosmic web that connects galaxies across billions of light-years. This idea highlights the interconnectedness of the universe and how its edges might hold clues to its overall architecture. The significance of the Great Attractor extends beyond its gravitational pull. By studying it, scientists hope to uncover more about dark matter and dark energy, the invisible forces that shape the universe's expansion and structure. Understanding these forces could provide insights into the ultimate fate of the cosmos, and whether the universe's edge is truly a boundary or just a point in an endless expanse. As we delve into the mystery of the Great Attractor, we're reminded of how much remains unknown about the universe's edges. This enigmatic region challenges us to explore further, pushing the boundaries of our knowledge and inspiring us to uncover the hidden forces that govern the cosmos. Now stepping into the realm of cosmic emptiness, let's turn our attention to the void regions of space. These vast, seemingly empty expanses are scattered throughout the universe, often spanning hundreds of millions of light-years. Far from being simple absences of matter, these voids play a crucial role in shaping the structure of the cosmos and may even hold clues about the nature of the universe's edge. One of the most famous examples is the Boötes Void, a colossal region located about 700 million light-years from Earth, often referred to as the Great Nothing. This void stretches across an astonishing area of space with a diameter of roughly 330 million light-years. What makes the Boötes Void so remarkable is its extreme lack of galaxies. While most regions of the universe are teeming with galaxies, this void contains only a handful, making it one of the emptiest places we've ever discovered. The existence of such voids challenges our understanding of how matter is distributed in the universe. According to the Big Bang Theory, the early universe was a hot, dense soup of particles. As it expanded and cooled, gravity gradually pulled matter together to form galaxies, stars, and planets. However, the presence of these immense voids suggests that the process wasn't uniform. Some regions were left almost entirely devoid of matter, creating these vast, empty spaces. Scientists believe that voids like the Boötes Void are a key part of the cosmic web, the large-scale structure of the universe. This web consists of dense filaments of galaxies and galaxy clusters connected by thinner threads of matter, with voids occupying the gaps between them. By studying these voids, researchers can gain insights into how the cosmic web formed and evolved over billions of years. Interestingly, these voids might also shed light on the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. Because voids are less dense than other regions, the effects of dark energy are more pronounced in them. By observing how voids grow and change over time, scientists can test theories about dark energy and its influence on the universe's ultimate fate. The study of void regions also raises intriguing questions about the universe's edge. If voids are areas where matter is sparse, could they mark the boundaries of the observable universe? Or are they simply part of an infinite, ever-expanding cosmos? These questions remind us that even the emptiest regions of space are filled with mysteries waiting to be unraveled. As we explore the void regions of space, we're reminded that emptiness can be just as fascinating as abundance. These vast cosmic deserts challenge our assumptions and inspire us to look deeper into the fabric of the universe, uncovering secrets that may redefine our understanding of existence itself. Now shifting our gaze to the intricate tapestry of the cosmos, let's explore the cosmic web, the large-scale structure that defines the universe's architecture. Picture the universe not as a random scattering of galaxies, but as an interconnected network, much like a spider's web, with galaxies and clusters linked by filaments of matter and separated by vast voids. This cosmic web is the result of billions of years of evolution, shaped by the forces of gravity and dark energy. At its core, the cosmic web is made up of three main components: dense knots of galaxies, thinner filaments connecting these knots, and the enormous voids that fill the spaces in between. The knots are where galaxies and galaxy clusters are most concentrated, acting as the hubs of this cosmic network. The filaments, on the other hand, are like bridges, guiding the flow of matter and energy across vast distances. And the voids, as we've discussed earlier, are the empty regions that make up most of the universe's volume. This structure didn't form overnight. It's the product of the universe's expansion and the gravitational pull of dark matter. In the early universe, tiny fluctuations in density caused matter to clump together. Over time, gravity amplified these clumps, pulling more matter into dense regions while leaving behind emptier spaces. Dark energy, meanwhile, accelerated the universe's expansion, stretching the web into its current form. Understanding the cosmic web is crucial for grasping the universe's boundaries and edges. The web's filaments and voids aren't just random features, they are the result of the universe's fundamental laws and its history. By studying the web, scientists can map the distribution of matter across the cosmos and infer the universe's overall shape and size. This, in turn, helps us answer questions about whether the universe is finite or infinite, and what lies beyond the observable edge. The cosmic web also provides a framework for exploring some of the universe's greatest mysteries, such as the nature of dark matter and dark energy. The way galaxies move within the web, for instance, can reveal the presence of unseen dark matter. Similarly, the growth of voids over time offers clues about dark energy's influence on the universe's expansion. As we unravel the secrets of the cosmic web, we gain a deeper appreciation for the universe's complexity and beauty. It's a reminder that even on the largest scales, the cosmos is governed by patterns and connections that continue to challenge and inspire our understanding of existence. Now turning to the enigmatic concept of spacetime, let's unravel what it truly means to approach its edge. Spacetime, as described by Einstein's theory of general relativity, is the fabric of the universe, a four-dimensional framework that combines the three dimensions of space with the dimension of time. It's this intricate weave that dictates how objects move and interact, from the smallest particles to the largest galaxies. But what happens when we approach the edge of spacetime? This question takes us into the realm of theoretical physics, where concepts like wormholes and spacetime singularities emerge. Wormholes, often depicted in science fiction, are hypothetical tunnels through spacetime that could connect distant regions of the universe, or even different universes altogether. While they remain unproven, the mathematics of general relativity suggests they could exist, offering a shortcut across the cosmos. Imagine folding a piece of paper so that 2 points touch. A wormhole would be like punching a hole through that fold, bridging the gap in an instant. Then there are spacetime singularities, points where the fabric of spacetime becomes infinitely curved and the laws of physics as we know them break down. The most famous example is the singularity at the center of a black hole, where gravity becomes so intense that not even light can escape. These singularities are not just cosmic oddities, they challenge our understanding of reality itself, pushing scientists to explore new theories like quantum gravity to make sense of what happens at such extremes. Reaching the edge of spacetime isn't just a physical journey, it's a philosophical one. It forces us to confront the limits of human knowledge and the possibilities that lie beyond. Could spacetime have boundaries, or is it infinite? If it does have an edge, what lies beyond it? Nothingness, alternate dimensions, or perhaps entire new universes? These questions push the boundaries of science and imagination. As we ponder these ideas, we're reminded that the universe is far stranger and more mysterious than we can comprehend. The edge of spacetime isn't just a frontier of exploration. It's a gateway to the unknown, inviting us to rethink everything we thought we knew about existence. Shifting our gaze to the marvels of modern technology, let's explore how the James Webb Space Telescope is transforming our understanding of the universe's edge. Launched in December 2021, this groundbreaking observatory is designed to peer deeper into space and further back in time than any telescope before it. Its advanced instruments allow it to observe the faintest light from the earliest galaxies, offering us a glimpse into the universe's infancy and the processes that shaped its boundaries. One of the most exciting discoveries from the James Webb Space Telescope has been the detection of galaxies that formed just a few 100 million years after the Big Bang. These ancient galaxies, located near the edge of the observable universe, challenge our existing theories about how quickly structures in the cosmos emerged. By studying these distant objects, scientists are piecing together the timeline of cosmic evolution and refining their understanding of the universe's earliest moments. But the telescope's contributions go beyond just observing distant galaxies. It is also shedding light on the mysterious forces that shape the universe's edge, such as dark matter and dark energy. By mapping the distribution of galaxies and measuring how their light is distorted by gravitational lensing, the James Webb Space Telescope is helping scientists trace the invisible web of dark matter that holds the cosmos together. Similarly, its observations of distant supernovae are providing new insights into the accelerating expansion of the universe, driven by the enigmatic force of dark energy. Perhaps most intriguing is the telescope's potential to uncover phenomena we haven't even imagined. Its ability to detect the chemical compositions of exoplanet atmospheres, for instance, could reveal clues about the conditions necessary for life, or even evidence of life itself, beyond our solar system. And as it continues to explore the universe's edge, it may discover new cosmic structures or physical laws that reshape our understanding of reality. The James Webb Space Telescope is more than just a tool for observation. It's a bridge to the unknown, connecting us to the farthest reaches of space and time. With each discovery, it brings us closer to unraveling the mysteries of the universe's edge, reminding us that the cosmos is vast, complex, and endlessly fascinating. As we follow its gaze into the depths of space, we're not just exploring the universe, we're exploring the very limits of human knowledge. Now turning to the limits of human perception, we find ourselves face to face with one of the most profound mysteries of the universe's edge, our own inability to fully grasp it. As much as we advance in technology and knowledge, our senses and cognitive abilities are inherently confined by the boundaries of our biology. We perceive the universe through the lens of our limited senses, which evolved not to comprehend the cosmos but to navigate our immediate environment. This raises the question, can we ever truly understand the edge of the universe, or are we forever constrained by the limitations of our own minds? From a scientific perspective, our tools and instruments extend our perception far beyond what our senses alone can achieve. Telescopes like the James Webb Space Telescope allow us to see galaxies billions of light-years away, while particle accelerators probe the smallest building blocks of matter. Yet, even with these powerful tools, we're still interpreting the universe through the framework of human understanding. Theories like quantum mechanics and relativity challenge our intuitive grasp of reality, suggesting that the true nature of the cosmos might be far stranger than we can imagine. Philosophically, the limits of human perception invite us to question the very nature of reality. Renowned thinkers like Immanuel Kant argued that our perception of the world is shaped by the structures of our mind, meaning we can never truly know the universe as it is in itself. This idea, known as transcendental idealism, suggests that the universe's edge and perhaps the universe itself may lie forever beyond our comprehension. Are we limited by the finite nature of our brains, or is there a possibility that future advancements could one day allow us to transcend these barriers? Interestingly, some scientists and philosophers propose that our perception might be expanded through technological augmentation or even artificial intelligence. Imagine a future where we merge with machines, enhancing our cognitive abilities to process complex cosmic phenomena. Or consider the possibility that advanced AI, unbound by human limitations, could uncover truths about the universe's edge that we've never been able to fathom. While these ideas venture into the realm of speculation, they remind us that the limits of perception are not necessarily fixed. As we ponder these questions, we're reminded that the mysteries of the universe's edge are as much about our own limitations as they are about the cosmos itself. The more we learn, the more we realize how little we truly know. But perhaps it's this very unknowability that drives our curiosity, pushing us to explore, question, and imagine. The edge of the universe may remain elusive, but in seeking to understand it, we're also pushing the boundaries of what it means to be human. Now shifting our focus, we delve into the remarkable role mathematics plays in helping us understand the edge of the universe, a frontier we cannot directly observe. Mathematics serves as the language of the cosmos, allowing us to model and predict phenomena that lie far beyond the reach of our telescopes and instruments. Through equations, formulas, and abstract concepts, mathematicians and physicists have crafted frameworks that offer glimpses into the universe's most enigmatic boundaries. Take, for example, string theory, a mathematical framework that attempts to unify all fundamental forces of nature. By proposing that particles are not points but tiny, vibrating strings, this theory suggests that the universe's fabric is woven from these intricate threads. While string theory remains unproven, its mathematical elegance provides a potential pathway to understanding the universe's edge, where conventional physics breaks down. The theory hints at dimensions beyond the familiar three, opening up new possibilities for what lies at the boundaries of our observable universe. Similarly, quantum mechanics, another cornerstone of modern physics, relies heavily on mathematics to describe the behavior of particles at the smallest scales. The equations of quantum mechanics reveal a universe that is probabilistic and uncertain, challenging our classical notions of space and time. At the edge of the universe, where extreme conditions prevail, these quantum effects might dominate, offering clues to its true nature. Mathematics allows us to explore these extreme scenarios, even if we cannot yet observe them directly. But mathematics does more than just describe the universe, it helps us ask the right questions. By creating models and simulations, scientists can test hypotheses about the universe's shape, size, and ultimate fate. For instance, mathematical models of cosmic inflation suggest that the universe expanded exponentially in its early moments, shaping the large-scale structure we see today. These models also raise intriguing questions about what lies beyond the observable universe, hinting at regions that may forever remain hidden from our view. Yet, mathematics is not without its limits. While it provides powerful tools for understanding, it cannot replace the need for observational evidence. Theories like string theory and quantum mechanics, for all their mathematical beauty, still require experimental validation. This interplay between theory and observation is what drives our quest to understand the universe's edge, reminding us that mathematics is a guide, not a final answer. As we continue to explore the mysteries of the cosmos, mathematics remains an indispensable ally, offering insights into realms that defy direct observation. It challenges us to think beyond our senses, to imagine possibilities that stretch the limits of our understanding. And in doing so, it brings us closer to unraveling the profound enigma of the universe's edge. Now shifting our perspective, let's ponder one of the most mind-bending questions in cosmology. Is the universe infinite, or does it have an edge? The concept of infinity has fascinated thinkers for centuries, but when applied to the cosmos, it becomes a profound mystery that challenges our understanding of space, time, and existence itself. If the universe is infinite, it means that no matter how far we travel, we'll never reach an edge. Space stretches endlessly in all directions, with no boundary to define its limits. This idea aligns with certain mathematical models and observations, such as the flat geometry of the universe suggested by the cosmic microwave background radiation. A flat universe often implies infinite space, where galaxies, stars, and cosmic structures extend forever into the void. But infinity is not just a mathematical concept, it carries profound implications. If the universe is infinite, it could mean that every possible configuration of matter and energy exists somewhere, leading to the possibility of infinite versions of stars, planets, and even beings like ourselves. On the other hand, if the universe is finite, it raises questions about what lies beyond its edge. Does space simply stop, or does it curve back on itself in some higher dimensional geometry? A finite universe could take the shape of a sphere, where traveling far enough in one direction might bring you back to your starting point, much like circumnavigating the Earth. This idea is supported by theories of a closed universe, where space-time curves in on itself, creating a cosmic loop without boundaries. Both scenarios, finite and infinite, come with their own set of challenges. An infinite universe defies our intuition, as our minds struggle to grasp something without limits. A finite universe, meanwhile, forces us to confront the nature of its boundaries. What lies beyond the edge? Is there nothingness, or does another reality exist? These questions push the boundaries of science and philosophy, reminding us that the cosmos remains a realm of profound mystery. As we explore these ideas, we're reminded that the concept of infinity is not just about the universe's size, but also its potential. Whether finite or infinite, the universe continues to inspire awe and curiosity, inviting us to imagine the unimaginable and to keep searching for answers at the very edge of existence. Delving deeper into the cosmos, let's explore the fascinating process of galaxy formation near the edge of the observable universe. Here, in the farthest reaches of space, galaxies are born and evolve in ways that challenge our understanding of cosmic structures. These distant galaxies, some of the earliest to form after the Big Bang, act as cosmic time capsules offering glimpses into the universe's infancy. The birth of galaxies is a complex dance of gravity, gas, and dark matter. In the early universe, tiny fluctuations in density allowed matter to clump together, forming the seeds of future galaxies. Dark matter, an invisible and mysterious substance, played a crucial role in this process. Its gravitational pull acted as a cosmic scaffold, drawing ordinary matter like hydrogen and helium into denser regions. Over billions of years, these regions collapsed under their own gravity, igniting the first stars and giving rise to galaxies. Near the edge of the observable universe, we find some of the oldest and most distant galaxies ever detected. These ancient structures are often smaller and less organized than modern galaxies, resembling cosmic infants still in their formative stages. Studying them helps us piece together the story of how galaxies grow and change over time. Dark energy also plays a pivotal role in this cosmic narrative. As the universe expands, dark energy accelerates this expansion, stretching space itself. This affects how galaxies evolve near the edge of the observable universe. Over time, the increasing expansion rate pulls galaxies farther apart, making it harder for them to interact or merge. This process shapes the large-scale structure of the universe, creating the intricate cosmic web we observe today. By examining these distant galaxies, scientists gain valuable insights into the early universe and the forces that shaped it. Each discovery brings us closer to understanding the complex interplay between dark matter, dark energy, and the birth of cosmic structures. As we peer into the depths of space, we're reminded that the universe's edge is not just a boundary but a window into the past, offering clues to the origins of everything we see. Now shifting our gaze to one of Einstein's most mind-bending predictions, we explore the phenomenon of time dilation and its profound impact on our understanding of the universe's edge. Time dilation, a cornerstone of Einstein's theory of relativity, reveals that time doesn't flow at the same rate everywhere. Instead, it can stretch or shrink depending on two key factors, gravity and velocity. Near massive objects like black holes, gravity warps spacetime so intensely that time slows down dramatically. Imagine an astronaut falling toward a black hole while you observe from a safe distance. From your perspective, the astronaut's movements would appear to slow to a crawl as their clock ticks far slower than yours. This bizarre effect isn't just theoretical, it's been confirmed by experiments and observations, like atomic clocks running slightly slower at Earth's surface compared to those in orbit. At the edge of the universe, where extreme conditions like black holes and relativistic speeds come into play, time dilation becomes a crucial factor in how we perceive cosmic events. For instance, light emitted from near the event horizon of a black hole takes longer to reach us, making events there appear to unfold in slow motion. Similarly, as objects approach the speed of light, time for them slows down relative to an outside observer. This means that if we could travel close to the speed of light, what might feel like a few minutes for us could correspond to thousands of years for those watching from Earth. Time dilation also complicates our understanding of the universe's edge. As we observe distant galaxies and cosmic events, the effects of gravity and velocity mean we're not seeing them as they are now, but as they were millions or even billions of years ago. This time delay, combined with the stretching of light due to the universe's expansion, creates a cosmic mirage that obscures our view of the true nature of the universe's boundaries. By unraveling the mysteries of time dilation, scientists gain deeper insights into the fabric of space-time and the forces that shape the cosmos. It reminds us that the universe's edge isn't just a question of distance but also of time, a dimension that bends and twists in ways that continue to challenge our understanding of reality. Now venturing into the quantum realm, we uncover the fascinating behavior of particles at the edge of the universe and the profound questions it raises about reality itself. Quantum particles, the building blocks of the cosmos, don't play by the same rules as larger objects. Instead, they exist in a world of probabilities and uncertainties, governed by the strange principles of quantum mechanics. At the edge of the universe, where space-time stretches to its limits, the behavior of these particles becomes even more enigmatic. For instance, quantum particles can exist in multiple states simultaneously, a phenomenon known as superposition. This means that at the universe's edge, a particle could be in multiple places or states at once, challenging our classical understanding of space and time. Another mind-bending aspect is quantum entanglement, where particles become so deeply connected that the state of one instantly influences the other, no matter the distance separating them. At the universe's edge, this phenomenon could suggest that space-time itself is woven together in ways we're only beginning to comprehend. If entangled particles maintain their connection across vast cosmic distances, it hints at a deeper layer of reality where space and time might be illusions or emergent properties rather than fundamental truth. Quantum tunneling adds another layer of mystery. Particles can seemingly tunnel through barriers that would be impossible to overcome under classical physics. At the edge of the universe, this could mean particles appearing in regions of space-time that, according to our current understanding, should be inaccessible. Such behavior could reshape our ideas about the boundaries of the cosmos and whether true edges even exist. By studying quantum particles at the universe's edge, scientists hope to unlock clues about the nature of reality itself. Do these particles reveal a deeper, more fundamental structure underlying spacetime? Could they hint at the existence of extra dimensions or a multiverse? The answers to these questions might lie in the quantum realm, where the rules of the universe bend and blur, offering a tantalizing glimpse into the true nature of existence. Shifting our gaze beyond the confines of our own universe, we encounter the mind-bending concept of the multiverse, a theory that suggests our universe might be just one among countless others. This idea fundamentally changes how we think about the edge of the universe, as it implies that what we perceive as the boundary might simply be a transitional point into another cosmic realm. Parallel universes, as theorized, could exist alongside our own, each with its own unique set of physical laws and conditions. Some might be strikingly similar to ours, while others could be wildly different, hosting realities we can scarcely imagine. The boundaries between these universes, however, remain one of the greatest mysteries. Are they sharply defined, or do they blur and overlap in ways we don't yet understand? One intriguing aspect of the multiverse is the idea that these parallel realities might be separated by what scientists call brains, short for membranes. These brains could exist in higher dimensions, invisible to us, yet serving as the walls between universes. If this is true, the edge of our universe might not be a physical barrier, but rather a threshold to another brain, opening the door to an infinite expanse of cosmic possibilities. Another theory suggests that the multiverse could be the result of eternal inflation, a process where new universes continuously bubble into existence within a larger cosmic fabric. In this scenario, the edge of our universe would simply mark the point where one bubble ends and another begins. This raises profound questions about what lies beyond our bubble. Could there be an endless sea of other universes, each with its own unique story? Exploring the multiverse also ties back to quantum mechanics, where every possible outcome of an event might spawn a new universe. This means that at the edge of our universe, where quantum effects dominate, the line between our reality and alternate ones could become increasingly blurred. Are these edges gateways to infinite versions of reality, or are they barriers that forever separate us from other cosmic realms? As we ponder the theoretical edge of the multiverse, we're left with more questions than answers. Could the multiverse be the ultimate answer to the mysteries of the universe's edge? Or does it simply push those mysteries into an even grander, more incomprehensible scale? Either way, the idea invites us to rethink not just the boundaries of our cosmos, but the very nature of existence itself. As we reach the end of our cosmic journey, it's time to reflect on the 25 mysteries we've explored about the edge of the universe. Each one challenges our understanding of existence, pushing the boundaries of what we thought was possible. From the observable universe's limits to the mind-bending concept of the multiverse, these mysteries remind us just how much we have yet to discover. The cosmic microwave background radiation offers a glimpse into the universe's infancy, while dark matter and dark energy shape its structure and future. Theories like the holographic principle and the Fermi paradox force us to rethink the nature of reality and our place within it. Even the James Webb Space Telescope, our most advanced tool, only scratches the surface of these profound questions. These mysteries aren't just scientific curiosities, they're windows into the fundamental truths of our cosmos. They invite us to question, to wonder, and to dream about what lies beyond the edge of our understanding. Could the universe be infinite, or is it just one piece of a grander multiverse? Do the voids and cosmic webs hold clues to the universe's true shape? And what might the end of the universe tell us about its beginning? Each mystery is a reminder that the universe is far stranger and more magnificent than we can imagine. As we close this exploration, I'd like to leave you with a question to ponder. If the edge of the universe is not a boundary but a doorway, what might we find waiting on the other side? Share your thoughts in the comments below. I'd love to hear your theories and ideas. And if you're as fascinated by these mysteries as I am, don't forget to subscribe and hit the notification bell. There's so much more to discover, and I can't wait to continue this journey with you. Until next time, keep looking up. The cosmos is waiting.